Welcome to Math for Sleep. It's lovely to have you here tonight. Before we begin our gentle exploration, I'd love to know where in the world you're settling in from. Perhaps you're tucked into a cozy bed with the curtains drawn, or maybe you're on a late evening train watching the world slip by in darkness, or possibly you're curled up on a comfortable couch with a warm drink nearby. Wherever you are, I hope you're feeling safe, comfortable, and ready to let your mind drift through one of mathematics' most beautiful mysteries. If you find value in these relaxing mathematical journeys and would like to hear more, a like and subscribe truly helps this quiet little channel continue creating these soothing explorations. And to those of you who are already part of this community, thank you. Your presence here means more than you might realize. Now tonight, we're going to wander through something quite special. We're going to explore patterns that never end, shapes that contain infinite complexity, and mathematical objects so strange and wonderful that they challenge everything we think we understand about space, size, and infinity itself. I'll try not to make it so fascinating that you lie awake thinking about it, but if I do, at least you'll have gained an appreciation for one of the most elegant concepts in all of mathematics, the concept of a pattern that repeats forever, yet never quite repeats the same way twice, a shape that you can zoom into endlessly and still find new details, a boundary that goes on infinitely, yet somehow contains a finite space. These aren't fantasies or philosophical puzzles. They're real mathematical objects with precise definitions and remarkable properties. So let's begin, shall we? Let's drift gently into the world of infinite patterns, where the simple becomes complex, where the finite contains the infinite, and where mathematics reveals a beauty that exists beyond our everyday experience. Imagine, if you will, that you are standing on a beach at dawn, watching the waves roll in. Each wave is different, yet each wave is somehow the same. There's a pattern there, but it's not a perfect repetition. It's something more subtle, more interesting. Now imagine looking down at the sand beneath your feet, noticing how it's made of countless tiny grains, each one irregular, yet together forming smooth curves and ripples. Zoom in closer with your mind's eye, and you might see that each grain itself has texture, tiny peaks and valleys, and if you could zoom in even further, you'd find molecules arranged in crystalline patterns, and deeper still, atoms dancing in their endless quantum waltz. This idea of patterns within patterns, of complexity hiding inside apparent simplicity, of structure that repeats across different scales. This is the essence of what mathematicians call self-similarity. It's the foundation of infinite patterns, and it's everywhere once you know how to look for it. But here's what makes mathematical infinite patterns so special, so different from the patterns we see in nature. In mathematics, we can take this idea of repetition and push it to its absolute limit. We can create patterns that truly never end, shapes that contain genuine infinity, not just a very large number of repetitions, but an actual infinite number. When we talk about infinite patterns in mathematics, we're usually talking about what are called fractals, though that's a relatively modern term coined by the mathematician Benoit Mandelbrot in 1975. The word comes from the Latin fractus, meaning broken or fractured, and it describes geometric shapes that are broken up in intricate ways, showing detail at every scale of magnification. But people had been discovering and studying these strange objects for much longer than that. Think about what happens when you look at a tree. The whole tree has a trunk that splits into major branches. Each of those branches splits into smaller branches. Those split into even smaller twigs. The twigs bear leaves, and if you look closely at a leaf, you'll see it has veins that branch in similar ways. It's not exactly the same pattern at every level, but there's a family resemblance, a kind of self-similarity that makes the whole thing recognizable as a tree. Nature, it seems, has discovered that branching patterns are efficient, elegant solutions to the problem of distributing resources, whether that's water and nutrients in a tree or blood in our circulatory system. But mathematical infinite patterns take this idea and refine it, perfect it, extend it beyond what nature can physically accomplish. In mathematics, we can create a pattern that branches forever, with no limit to how small the branches can get, no atomic scale where the pattern must finally stop. We can create boundaries that wiggle infinitely, perimeters that stretch on without end, even while enclosing a modest, finite space. We can build structures that have dimension that isn't a whole number, objects that exist somehow between the familiar worlds of lines and planes and solids. These mathematical objects were initially viewed with suspicion, even distaste, by mathematicians. They were considered pathological, monstrous, aberrations that violated the smooth, well-behaved geometry that had dominated mathematics since Euclid. But gradually, mathematicians came to realize that these strange, infinitely complex shapes weren't monsters at all. They were windows into a deeper understanding of mathematics, nature, and reality itself. They revealed that the mathematical universe was far richer, far stranger, and far more beautiful than anyone had imagined. The journey into infinite patterns begins with a simple question. What happens if you take a process, any process, and repeat it forever? What happens if you keep applying the same rule over and over without ever stopping? Sometimes the answer is boring. The pattern settles down into something predictable. Sometimes it explodes outward into chaos. But sometimes, beautifully, mysteriously, the pattern creates something new, something that couldn't exist after just a few repetitions, or 100 repetitions, or 1,000,000. Something that only emerges in the limit as the number of repetitions approaches infinity. This is where we're going tonight, into those mysterious limit spaces where infinity lives. We'll move slowly, carefully, one step at a time, building up these infinite patterns piece by piece, layer by layer, until we can glimpse the whole magnificent structure. We'll start with a snowflake, not a real one made of ice and water molecules, but a mathematical snowflake made of pure geometry and infinite iteration. And from there, we'll travel to triangles that eat themselves, to sets that contain uncountably many points, yet occupy zero space, to boundaries so complex that they can never be fully drawn or fully understood, only approximated, only approached. Let yourself relax into these ideas. Don't worry about understanding everything immediately. Let the concepts wash over you gently, like those waves on the beach we imagined earlier. Mathematics at this level isn't about calculation or memorization. It's about patterns, about beauty, about the strange and wonderful things that happen when we take simple rules and let them play out to their infinite conclusion. Let's begin our journey with one of the most elegant examples of an infinite pattern, a mathematical construction so visually striking and conceptually profound that it has become an icon of fractal geometry. We're going to build, step by step, what's known as the Koch snowflake, named after the Swedish mathematician Helge von Koch, who described it in 1904. Picture, if you will, a simple equilateral triangle, 3 straight sides, 3 equal angles. Nothing fancy. This is our starting point, our seed from which the infinite pattern will grow. Now, here's the rule we're going to apply. And it's beautifully simple. For each straight line segment in our shape, we're going to divide it into 3 equal parts. We'll leave the first and last thirds alone. But that middle third, we're going to replace it with 2 sides of a smaller equilateral triangle. Imagine taking that middle segment, removing it, and in its place, constructing a little triangular bump pointing outward. Let's walk through this carefully. Our original triangle has 3 sides. When we apply our rule to each side, we replace one straight line with 4 line segments, each 1/3 the length of the original. The middle third becomes the base of a little triangle that points outward, creating a 6-pointed star-like shape. This is the first iteration, the first step in our infinite process. Already, something interesting has happened. Our perimeter has grown. We started with 3 sides of some length. Let's say each side was 1 unit long, giving us a total perimeter of 3 units. After the first iteration, each unit long side has been replaced with 4 segments, each 1/3 of a unit long. So each original side now contributes 4/3 units to the perimeter. Multiply by 3 sides, and we have a total perimeter of 4 units. The perimeter has grown by a factor of 4/3. Now we do it again. Every single straight line segment in our star gets the same treatment. Each segment is divided into 3 equal parts, and the middle third is replaced with a triangular bump. After this second iteration, our shape has become considerably more intricate. What were once 6 points on our star have now become clusters of smaller points. The outline is starting to look less like a geometric construction and more like something organic, something almost natural. And the perimeter has grown again by another factor of 4/3. Let's think about what's happening here. Each time we apply our rule, we multiply the perimeter by 4/3. After 1 iteration, it's 4 units. After 2 iterations, it's 4 times 4/3, which is 16/3, or about 5.33 units. After 3 iterations, it's 4 times 4/3, times 4/3 again, which is 64/9, or about 7.11 units. Do you see the pattern? Each iteration multiplies the perimeter by 4/3. So after n iterations, the perimeter is 3 times 4/3 raised to the power of n. Now here's where it gets interesting, where the infinite nature of this pattern reveals itself. What happens if we keep going? What if we perform this operation not just 3 times, or 10 times, or 1,000 times, but infinitely many times? What is the limit of 3 times 4/3 to the nth power as n approaches infinity? Well, 4/3 is greater than 1, so raising it to larger and larger powers makes it grow without bound. The perimeter in the limit as we perform infinite iterations becomes infinite. We have created a shape with an infinitely long boundary. Let that sink in for a moment. We started with a simple triangle with a finite perimeter of 3 units. By applying a simple geometric rule over and over, infinitely many times, we've created a shape whose boundary is infinitely long. You could never finish walking around this snowflake, even though it's sitting right there on the page, a bounded region that you could enclose in a circle. Think about what this means. Imagine you wanted to trace the outline of this snowflake with a pencil. You'd start at some point and begin following all the little zigzags and bumps. But there are infinitely many of them, getting smaller and smaller as you zoom in, but always there, always adding more length to the boundary. You would never finish. Not if you trace for 1,000,000 years, not if you trace forever. But here's the truly remarkable thing. The property that makes the Koch snowflake so paradoxical and so beautiful. While the perimeter is infinite, the area enclosed by this snowflake is finite. It doesn't sprawl out to infinity. It stays neatly contained, a bounded region of the plane. How can this be? How can something with an infinite boundary contain only a finite area? Let's think about the area more carefully. When we add those little triangular bumps in each iteration, we're adding some area to our shape. The original triangle had some area. Let's call it A. When we add the first layer of bumps, we're adding 3 small triangles, each with an area that's 1/9 the area of the original triangle. Why 1/9? Because the side length of each small triangle is 1/3 the side length of the original, and area scales with the square of the side length. 1/3 squared is 1/9. So the first iteration adds 3/9, or 1/3 of the original area. Our total area is now A plus 1/3 A, or 4/3 A. In the second iteration, we add more little triangles, but these are even smaller. We're adding 1 small triangle to each of the 12 edges that exist after the first iteration. Each of these new triangles has a side length that's 1/3 the length of the segments from the first iteration, which were themselves 1/3 the length of the original. So these new triangles have side length 1/9 the original, and area 1/81 the original. 12 of them together add 12/81 of the original area, which simplifies to 4/27 of A. Do you see the pattern emerging? In each iteration, we're adding area, but the amount we add gets smaller with each step because the triangles get smaller. In the first iteration, we add 1/3 A. In the second, we add 4/27 A, which is 1/3 A times 4/9. In the third iteration, we'd add 1/3 A times 4/9 times 4/9. The total area is the original area A, plus all these additions. This forms a geometric series. We have A times the quantity, 1 plus 1/3 plus 1/3 times 4/9 plus 1/3 times 4/9 squared, and so on. The sum of a geometric series with first term A and common ratio R AR, when the absolute value of R is less than 1, is a divided by 1 minus R. In our case, we're summing 1 plus 4/9 plus 4/9 squared, and so on, where the first term is 1 and the common ratio is 4/9. This sum converges to 1 divided by 1 minus 4/9, which is 1 divided by 5/9, which is 9/5. So the total area is A times 1/3 times 9/5 for the added parts, which simplifies to 3/5. A for all the bumps added in all iterations. Add that to the original area A, and we get A times 8/5. The Koch snowflake, after infinite iterations, has an area exactly 8/5 times the area of the starting triangle. That's it, a specific finite number. We can calculate it exactly. Yet this shape, with its perfectly calculable finite area, has an infinite perimeter. It's a figure that lives in a flat two-dimensional plane, yet its boundary is so convoluted, so endlessly complex, that it reaches toward infinity. This is our first glimpse of the strange world of fractals and infinite patterns, a world where intuition breaks down, where the familiar rules of geometry stop applying in the ways we expect. The Koch snowflake looks like a snowflake, hence its name, with its six-fold symmetry and its delicate, intricate outline. But no real snowflake made of water molecules could ever have this structure, because real snowflakes are made of atoms, which have a finite size. You can't keep subdividing the arms of a real snowflake forever. Eventually, you reach the atomic scale and the subdivision must stop. But in mathematics, there is no atomic scale. Numbers can be divided infinitely. Geometric constructions can continue to arbitrary precision. The Koch snowflake is a purely mathematical object existing in the realm of perfect abstraction. Yet it helps us understand something deep about the nature of boundaries, of measurement, of the relationship between perimeter and area. It shows us that our intuitions, built from experience with smooth, well-behaved shapes like circles and polygons, can fail spectacularly when we venture into the realm of the infinite. There's something almost meditative about contemplating the Koch snowflake. Imagine zooming in on its boundary, closer and closer. You'd see the same pattern repeating at every scale. Small bumps made of smaller bumps, made of smaller bumps still, each one a miniature echo of the whole. This self-similarity, this property of looking the same at every level of magnification, is the hallmark of fractals. It's what gives them their strange beauty and their deep connection to natural phenomena. Because while perfect fractals can't exist in physical reality, many natural objects exhibit approximate fractal behavior over a range of scales. The branching of trees, the structure of coastlines, the shape of clouds, all show this kind of self-similar, scale-invariant structure. The Koch snowflake was one of the first fractals to be rigorously studied, and it opened the door to an entire field of mathematics. It showed that infinity could be tamed, studied, understood, at least in part. That infinite complexity could emerge from simple rules, that mathematics contained wonders that no one had imagined. As we lie here in the quiet, thinking about this mathematical snowflake with its infinite boundary and finite area, we're touching something profound. We're glimpsing infinity itself, not as an abstract concept or a vague notion of going on forever, but as a concrete mathematical reality with specific, calculable properties. Let's turn our attention now to another remarkable infinite pattern, one that's perhaps even stranger than the Koch snowflake. This is the Sierpinski triangle, named after the Polish mathematician Wacław Sierpinski, who described it formally in 1915. Though, like many mathematical discoveries, it had been explored in various forms long before that. The Sierpinski triangle has a haunting, almost mystical quality to it. It's a shape that seems to be consuming itself, hollowing itself out, becoming more and more insubstantial with each iteration, yet never quite disappearing entirely. Let's build it together, starting from the beginning, from the simplest possible starting point. Take an equilateral triangle, solid and filled in, sitting on a flat surface. This is our stage 0, our initial configuration. Now here's what we're going to do. And again, the rule is beautifully simple. We're going to find the midpoint of each of the 3 sides of our triangle. Connect those 3 midpoints to form a smaller triangle right in the center. Now here's the key part. We remove that central triangle. We cut it out, leave it blank, make it empty. We've taken our solid triangle and punched a triangular hole right through its middle. What are we left with? We now have 3 smaller solid triangles, each one sitting in a corner of the original, each one exactly half the size of the original in terms of side length, which means 1/4 the area. The 3 corners together contain 3/4 of the original area. 1/4 has been removed, vanished into the white space. This is the first iteration of the Sierpinski triangle construction. Already something interesting has happened. Our solid shape has developed an internal structure, a pattern, and we're going to apply the same rule again. Take each of those 3 remaining solid triangles. For each one, find the midpoints of its sides, connect them to form a smaller triangle in its center, and remove that central piece. After this second iteration, what do we have? Each of our 3 triangles from the first stage has become 3 even smaller triangles. So we now have 9 small, solid triangles arranged in a specific pattern with gaps between them. How much area remains? We started with 3/4 after the first iteration. In the second iteration, we removed 1/4 of each of the 3 remaining pieces. That's 3 times 1/4 of 3/4, which is 3/16. Subtracting from 3/4, we get 9/16 of the original area remaining. Let's keep going. Third iteration. Each of our 9 small triangles gets the same treatment. We remove the central quarter from each one, leaving 3/4 of each. We now have 27 tiny triangles arranged in an intricate pattern of solid regions and empty spaces. The area remaining is 3/4 of 9/16, which is 27/64. Do you see the pattern in these fractions? 3/4, 9/16, 27/64. The numerator is being multiplied by 3 each time, the denominator by 4. After n iterations, the area remaining is 3 to the nth power divided by 4 to the nth power, which we can write as 3/4 raised to the power n. Now let's ask the crucial question. What happens as we let n grow without bound? What happens when we perform this operation not just 3 times or 10 times, but infinitely many times? What is the limit of 3/4 to the nth power as n approaches infinity? Well, 3/4 is less than 1. So as we raise it to larger and larger powers, it gets smaller and smaller, approaching 0. In the limit, after infinite iterations, the Sierpinski triangle has area 0. Think about that. We've removed so much material, carved out so many holes, that nothing remains, at least in terms of area. And yet, the Sierpinski triangle is not empty. It's not nothing. There are still points there, infinitely many points in fact. Every corner of every small triangle at every stage of construction is a point in the final Sierpinski triangle. All the midpoints of all the edges at every stage are there. And it turns out there are many other points too. Points that aren't obviously special in the construction, but that nevertheless survive all the removals. The Sierpinski triangle is a set of points with 0 area but uncountably infinite cardinality, meaning it contains more points than there are counting numbers. More points than you could ever list in a sequence. How can this be? How can something have zero area but still contain infinitely many points, so many points that they can't even be counted? This is one of the deep mysteries that infinite patterns reveal. Our intuition about size and number breaks down. We think of more points as meaning larger area. But in the realm of mathematical infinite patterns, these concepts can come apart. The Sierpinski triangle occupies no area, takes up no space in the traditional sense. Yet it exists, it has structure, it has properties that can be studied and understood. Let's think about the perimeter of the Sierpinski triangle, or rather, the total length of all the boundaries between solid and empty regions. In the initial triangle, we have 3 sides forming a perimeter of length. Let's say 3 units if each side is 1 unit. In the first iteration, when we remove the central triangle, we create new internal boundaries. The central removed triangle has a perimeter of 1.5 units because its sides are each half a unit long. So our total boundary length increases to 4.5 units. In the second iteration, we remove 3 more triangles, each with sides 1/4 unit long, contributing 3 times 3/4, or 9/4 units of new boundary, for a total of about 6.75 units. With each iteration, we're adding more and more internal boundaries, and the total length of all boundaries grows without bound. Like the Koch snowflake, the Sierpinski triangle, in its infinite limit, has an infinite total boundary length, even though it occupies 0 area. It's a shape that's all perimeter and no interior, if you can wrap your mind around such a thing. The Sierpinski triangle has a quality that mathematicians call self-similarity in a very strong sense. If you take any one of the 3 main corner pieces after the first iteration and you zoom in on it, scale it up by a factor of 2, it looks exactly like the whole triangle. The Sierpinski triangle is made of 3 copies of itself, each scaled by 1/2. This self-similarity isn't just approximate or artistic, it's exact and mathematical, and it continues down through every scale. Each small triangle is made of 3 smaller triangles, each 1/4 the size, and those are made of even smaller triangles, and so on forever. This property of being made up of smaller copies of itself is what gives the Sierpinski triangle its fractal dimension. Without getting too deep into the technical details, which might disturb our gentle drift towards sleep, the idea is this. We usually think of dimensions as whole numbers. A line is 1-dimensional, a plane is 2-dimensional, a solid is 3-dimensional. But the Sierpinski triangle lives somewhere between 1 and 2 dimensions. It's more than a simple curve, but less than a solid region. Mathematicians can calculate its exact fractal dimension using the formula that relates the number of self-similar pieces to the scaling factor. For the Sierpinski triangle, made of 3 pieces each scaled by 1/2, the dimension works out to be log of 3 divided by log of 2, which is approximately 1.585. It's a fractional dimension, a dimension that's not a whole number, which is where the word fractal comes from. What does it mean to have a dimension of about 1.6? It means the Sierpinski triangle is, in a very real mathematical sense, more complicated than a line, but simpler than a plane. It's a glimpse of a geometry that exists between the familiar integer dimensions, a geometry that better describes many structures in nature than classical Euclidean geometry does. Think about a crumpled piece of paper. It's made of a two-dimensional sheet, but when it's crumpled, it occupies three-dimensional space in a complex way. Its effective dimension is somewhere between 2 and 3. Fractals give us the mathematical tools to describe and quantify this kind of in-between state. The Sierpinski triangle appears in unexpected places throughout mathematics. It shows up in Pascal's triangle when you color odd numbers differently from even numbers. It appears in certain cellular automata, simple computational systems where each cell evolves based on its neighbors according to fixed rules. It emerges from something called the chaos game, where you start with a point and repeatedly move it halfway toward randomly chosen vertices of a triangle. After thousands of iterations, the points fill in a perfect Sierpinski triangle. This emergence of order from randomness, of pattern from chaos, is one of the beautiful mysteries of fractals. As you lie here contemplating the Sierpinski triangle, imagine zooming into it, deeper and deeper. At each level of magnification, you'd see the same triangular pattern, the same arrangement of solid and void repeating endlessly. There's no smoothing out, no level at which it becomes simple or featureless. The complexity is infinite, but it's a structured, patterned infinity. It's not random noise or chaotic scribbling. It's organized, mathematical, beautiful. The Sierpinski triangle is a reminder that absence can have structure, that emptiness can have pattern, that zero can contain infinity. We're going to take a brief detour now, away from triangles and snowflakes, to visit one of the most philosophically profound mathematical objects ever conceived. This is the Cantor set, named after Georg Cantor, who introduced it in 1883, though credit for its discovery is sometimes also given to Henry John Stephen Smith, who found it independently around the same time. The Cantor set is, in some ways, the simplest of all fractals, and yet it reveals truths about infinity that are so strange they initially drove some mathematicians to distraction. Let's begin, as we always do, with something simple. Imagine a line segment, specifically the interval from 0 to 1 on the number line. Every real number between 0 and 1, including both endpoints. This is a continuum, an uncountable infinity of points all lined up, forming a solid line segment of length 1. This is our starting configuration. Now here's what we're going to do. We're going to remove the middle third of this interval, not including the endpoints of the removed part, just the open middle third. What does that mean exactly? The interval from 0 to 1 can be divided into 3 equal parts: 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. We're going to remove the open middle interval, the points strictly between 1/3 and 2/3, not including 1/3 itself or 2/3 itself, but everything in between. After this first step, we're left with 2 intervals, from 0 to 1/3 and from 2/3 to 1. Each of these has length 1/3, so the total length of what remains is 2/3. Now we repeat the process. For each remaining interval, we remove its open middle third. From the interval 0 to 1/3, we remove the points from 1/9 to 2/9. From the interval 2/3 to 1, we remove the points from 7/9 to 8/9. After this second iteration, we have 4 intervals remaining, each of length 1/9, for a total remaining length of 4/9. Then we do it again, and again, and again. With each iteration, we're removing more pieces, and the total length remaining is shrinking. Let's think about how much we're removing at each step. In the first iteration, we remove one interval of length 1/3. In the second, we remove two intervals, each of length 1/9, for a total removed length of 2/9. In the third iteration, we remove four intervals of length 1/27, for a total of 4/27. Pattern is clear. In the nth iteration, we remove 2 to the power of n-1 intervals, each of length 1/3 to the power of n. The total amount removed across all iterations is the sum of 1/3 plus 2/9 plus 4/27, and so on. This is a geometric series with first term 1/3 and common ratio 2/3. The sum of an infinite geometric series with first term a and ratio ER, where the absolute value of r is less than 1, is a divided by 1 minus r. Plugging in our values, we get 1/3 divided by 1 minus 2/3, which is 1/3 divided by 1/3, which equals 1. We've removed a total length of 1, everything. But wait, we started with an interval of length 1, and we've removed length 1. So what's left? The Cantor set, and it has measure 0, meaning its total length is 0. Yet the Cantor set is not empty. In fact, it contains infinitely many points. Where are these points? Well, think about the endpoints of all the intervals at each stage of construction. The number 1/3 is never removed. It's the endpoint of an interval that stays at every stage. Same with 2/3 and 1/9 and 2/9 and 7/9 and 8/9 and all the other endpoints. These are all in the Cantor set. But there's more. It turns out the Cantor set contains far more than just these endpoints. There are uncountably many points in the Cantor set, just as many points as there were in the original interval from 0 to 1. How can this be? How can we remove a total length equal to the whole interval, yet still have uncountably many points left? This is where our intuitions about infinity begin to strain and bend. The Cantor set is a profound example of how infinite sets can have properties that seem contradictory or impossible from a finite perspective. Here's one way to think about which numbers are in the Cantor set. Consider writing numbers in base 3 instead of base 10. In base 3, we use only the digits 0, 1, and 2. Every number between 0 and 1 can be written as a base 3 decimal. For instance, 1/3 in base 3 is 0.1, meaning 1/3 to the first power. 2/3 is 0.2. The number 1/9 is 0.01, and so on. Now, in the first step of constructing the Cantor set, we removed the middle third, which is all numbers whose base 3 expansion starts with a 1. We keep the numbers that start with 0 and the numbers that start with 2. In the second step, we remove the middle third of each remaining piece. This corresponds to removing numbers whose base 3 expansion has a 1 in the second position after the decimal point, provided the first position was either 0 or 2, and so on. After infinite iterations, the Cantor set consists precisely of all numbers between 0 and 1 whose base 3 expansion can be written using only zeros and 2s with no ones at all. Now, how many such numbers are there? Well, each position after the decimal point in base 3 can be either 0 or 2, giving us 2 choices for each position. There are infinitely many positions, so we have 2 choices, infinitely many times. This gives us an uncountable infinity of numbers, just as many as all the real numbers between 0 and 1. The Cantor set is uncountable, despite having 0 length. It's a dust of points, infinitely sparse, yet infinitely dense in a different sense. The Cantor set has another remarkable property. It's what mathematicians call a perfect set, meaning every point in the Cantor set is a limit point of other points in the set. You can get arbitrarily close to any point in the Cantor set using other points from the Cantor set. Despite having 0 length, despite being scattered across the interval in this highly disconnected way, the Cantor set has no isolated points. Every point is surrounded, in a sense, by infinitely many other points from the set. It's a closed set with no interior, a nowhere dense set that's nevertheless uncountable and perfect. Why do mathematicians care about such a strange object? Because the Cantor set is a powerful tool for constructing counterexamples and understanding subtle properties of real analysis and topology. It shows that our intuitions about size, measure, and cardinality can diverge in extreme ways. Something can be infinitely large in terms of the number of points it contains, yet infinitely small in terms of the space it occupies. The Cantor set is a window into the deep structure of the real number line, revealing complexities that aren't apparent from casual observation. There are many variations on the Cantor set. Instead of removing the middle third at each stage, we could remove different proportions, creating what are called fat Cantor sets that have positive measure, or skinny Cantor sets that shrink even faster than the standard middle thirds version. We can construct similar sets in higher dimensions, creating Cantor dust in the plane or in space, objects with 0 area or volume, but still containing uncountably many points. These constructions have found applications in dynamical systems, probability theory, and even in understanding strange attractors in chaos theory. As you rest here, thinking about the Cantor set, imagine the number line, that infinite straight path from negative infinity to positive infinity. Focus on the segment from 0 to 1. Now imagine taking away pieces, carefully, systematically, leaving behind only the ghostly framework of endpoints and carefully chosen points. What remains is invisible, in a sense, occupying no length. Yet it's still there, still real, still mathematically meaningful. The Cantor set is a meditation on what it means for something to exist. It has 0 size, but infinite cardinality. It's nowhere yet everywhere dense in its own peculiar way. It's a mathematical poem about absence and presence, about the infinitely large and the infinitesimally small. Now we come to perhaps the most famous mathematical infinite pattern of all, an object so visually stunning and conceptually rich that it has transcended mathematics to become a cultural icon. This is the Mandelbrot set, and it exists not on a line or in the familiar flat plane we've been working with, but in the complex plane, that strange two-dimensional space where numbers have both a real part and an imaginary part. Don't worry, we'll approach this gently, building up to it piece by piece, and you don't need to understand all the technical details to appreciate its remarkable beauty. Let's start with complex numbers. You've probably heard of imaginary numbers, numbers involving the square root of -1, which mathematicians denote by the letter I. A complex number is simply a real number plus an imaginary number. We write them in the form a plus by, where a and b are real numbers. For instance, 3 plus 4, Ri, is a complex number. The number A is called the real part, and B is called the imaginary part. We can visualize complex numbers by plotting them on a plane, with the real part on the horizontal axis and the imaginary part on the vertical axis. This is the complex plane, and it's the stage on which the Mandelbrot set performs its infinite drama. Now, the Mandelbrot set is defined by a very simple rule involving iteration, just like the fractals we've already explored. Here's the rule. Take a complex number C, any complex number. Start with z equals 0. Then repeatedly apply the formula. Replace z with z squared plus c. In other words, square whatever z currently is, then add c. Do this over and over. What happens? Does the sequence of z values stay bounded, remaining within some finite distance from the origin? Or does it escape to infinity, growing larger and larger without bound? The Mandelbrot set is the collection of all complex numbers C, for which this iteration process stays bounded. If starting from z equals 0 and repeatedly applying z goes to z squared plus c keeps the values of z from flying off to infinity, then C is in the Mandelbrot set. That's it. That's the definition. But from this simple rule emerges a shape of unbelievable complexity and beauty. Let's try a few examples to get a feel for this. Suppose C equals 0. Then we start with z equals 0, and we keep computing z squared plus c, which is just z squared. 0 squared is 0, so z stays at 0 forever. The sequence is 0, 0, 0 forever. It definitely stays bounded, so 0 is in the Mandelbrot set. Now try c equals 1. We start with z equals 0. First iteration, 0 squared plus 1 equals 1. Second iteration, 1 squared plus 1 equals 2. Third iteration, 2 squared plus 1 equals 5. Fourth iteration, 5 squared plus 1 equals 26. The numbers are growing rapidly, clearly heading toward infinity. So 1 is not in the Mandelbrot set. What about c equals -1? Starting from z equals 0, we get 0 squared plus -1 equals -1. Then -1 squared plus -1 equals 1 minus 1 equals 0. Then 0 squared plus -1 equals -1 again. The sequence is 0, -1, 0, -1, alternating forever. It's bounded, cycling between two values. So -1 is in the Mandelbrot set. You can try other values of c and see whether the iteration stays bounded or escapes. For some values, it quickly becomes obvious that the sequence is exploding to infinity. For others, it settles into a cycle or stays near the origin. When mathematicians computed this for thousands of values of c across the complex plane and colored the points based on whether they're in the set or not, something miraculous appeared. The Mandelbrot set has a recognizable main body, a roughly circular region called the main cardioid, with a smaller circular bulb attached to its left. From these, intricate filaments and tendrils extend outward, decorated with an infinite variety of smaller structures. There are spiral arms, seahorse valleys, elephant valleys, and countless other regions, each with its own character, each containing infinite complexity. What makes the Mandelbrot set truly extraordinary is its boundary. The edge between points that are in the set and points that are not is infinitely intricate. If you zoom in on any part of the boundary, you find more detail, more structure, patterns within patterns, forever. And here's the thing. Not only does the boundary never smooth out or become simple, but as you zoom in, you often find miniature copies of the entire Mandelbrot set, nested deep within the boundary structure. Tiny versions of the whole set, complete with their own main body and tendrils. And if you zoom into those miniatures, you find even tinier copies, on and on without end. This is self-similarity taken to an extreme. The Mandelbrot set isn't strictly self-similar like the Koch snowflake or Sierpinski triangle, where the same exact pattern repeats at every scale. Instead, it's almost self-similar, with each zoomed-in region revealing structures that are similar to, but not quite identical to the whole. There are common motifs, spirals that appear again and again, but with variations, with embellishments, with unique local character. It's been compared to exploring an infinitely detailed coastline, where every promontory and inlet contains further promontories and inlets forever. The Mandelbrot set was discovered, or perhaps more accurately, first clearly seen and understood by Benoit Mandelbrot in 1979 and 1980, while he was working at IBM Research. He was studying the iteration of complex quadratic polynomials, following up on earlier work by mathematicians like Pierre Fatou and Gaston Julia from the early 20th century. But it was the advent of computer graphics that allowed Mandelbrot to actually visualize the set and see its structure. Before computers, mathematicians could study the properties of such iterations theoretically, but they couldn't see the big picture, couldn't witness the stunning visual complexity that the Mandelbrot set displays. When images of the Mandelbrot set first appeared, they caused a sensation. Here was a mathematical object of astounding beauty, created by a simple rule, yet containing infinite variety. It looked organic, almost alive, with structures resembling tendrils, flowers, fireworks, sea creatures. It inspired art, music, philosophy. It became a symbol of the hidden depths of mathematics, proof that simple rules could generate unlimited complexity, that the mathematical universe was far richer and stranger than anyone had imagined. The boundary of the Mandelbrot set is believed, though not yet proven rigorously, to have a fractal dimension of 2. That means it's so convoluted, so space-filling, that in some sense it's more than a one-dimensional curve. It's approaching two-dimensionality through sheer intricacy. The set itself has area 0 in a certain technical sense, yet its boundary has this higher dimensional complexity. And the boundary is connected, meaning you can travel from any point to any other point along the boundary without leaving it, despite all the fragmentation and filigreed structure. There are deep connections between the Mandelbrot set and Julia sets, which are related fractal sets defined for each complex number. For each point C in the complex plane, there's a Julia set associated with the iteration Z goes to Z squared plus C. The Mandelbrot set is, in a sense, a map of all Julia sets. Points in the Mandelbrot set correspond to connected Julia sets, while points outside correspond to disconnected Julia sets. The Mandelbrot set is a parameter space, a catalogue of behaviors for this simple quadratic iteration. Exploring the Mandelbrot set is like exploring an infinite alien landscape. Software exists that lets you zoom into the set, magnifying the view by factors of millions or billions or more. As you zoom, the fractal nature means the detail never runs out. You can zoom for hours, descending through layers upon layers of structure, and always find new patterns, new miniatures, new surprising formations. Some regions have been explored and named, There's the Seahorse Valley, characterized by spiral structures resembling seahorses. There's the San Marco Fractal, resembling the facade of a cathedral. There are Julia Islands, mini Mandelbrots, spiral galleries, and countless unnamed regions waiting to be discovered. The Mandelbrot set reminds us that mathematics is not just about calculation and proof. It's about discovery and beauty. Mandelbrot himself emphasized the visual and intuitive aspects of mathematics, arguing that fractals provided a new geometry for describing nature, more appropriate for describing clouds, mountains, and coastlines than classical Euclidean shapes like circles and triangles. The Mandelbrot set is the icon of this new geometry, a perfect mathematical object that seems to bridge the abstract and the organic, the calculated and the natural. As you lie here, imagine zooming into the Mandelbrot set. Picture descending into one of its spirals, watching it bloom into ever more intricate forms, seeing miniature Mandelbrots appear, and then seeing even tinier ones within those. Imagine the boundary rippling and folding, creating spaces and voids, generating pattern after pattern after pattern, forever. There's something hypnotic about it, something that speaks to a deep part of our pattern-seeking minds. The Mandelbrot set is an infinity that you can hold in your mind, visualize, explore. It's a mathematical object that invites contemplation, that rewards attention with beauty. We've been dwelling in the realm of pure mathematics, constructing infinite patterns through precise geometric rules and abstract iterations. But fractals aren't just mathematical curiosities. They appear throughout nature, often in approximate or statistical forms, giving structure to the world around us. The rules that govern growth and formation in the natural world often lead to fractal-like patterns, suggesting that these infinite self-similar structures are not just elegant mathematical constructions, but fundamental patterns of reality itself. Think about a tree standing in a forest. The overall shape of a tree, its branching structure, displays clear fractal properties. The trunk splits into major branches. Each major branch splits into smaller branches. Those split into twigs, and the twigs bear leaves. At each level of this hierarchy, the pattern is similar, splitting, diverging, reaching outward. This isn't a perfect mathematical fractal, obviously. The branches don't split at exactly the same angles or in exactly the same proportions. Real trees are subject to wind, competition for light, damage, random variation. But statistically, on average, trees exhibit self-similar branching across multiple scales. Why do trees grow this way? Because branching is an efficient solution to the problem of distribution. A tree needs to transport water and nutrients from its roots to its leaves, and transport sugars from its leaves back down. A branching network allows these resources to reach every part of the tree through a connected system of vessels. And branching patterns naturally lead to fractal-like structures because the constraints at each level are similar. Divide the flow, reach out in multiple directions, maximize surface area for the next level of subdivision. Look closer at individual leaves on that tree. Many leaves show fractal vein patterns, smaller veins branching off from larger ones, creating a hierarchical network that distributes water and nutrients throughout the leaf tissue. Some plants take this to extremes. Ferns are famous for their fractal-like structure, where each frond is divided into smaller fronds, which are divided into even smaller frondlets, creating that characteristic feathery appearance. Romanesco broccoli is an even more striking example, a vegetable whose florets are arranged in a spiral pattern, with each floret itself composed of similar spiral arrangements, creating a naturally occurring fractal that looks like it was designed by a mathematician. Rivers and their tributaries form branching networks that are statistically fractal. A major river is fed by smaller rivers, which are fed by streams, which are fed by brooks and creeks, creating a hierarchical drainage network across a landscape. From space, river systems look remarkably similar at different scales, showing that self-similar branching pattern we've been exploring. The reason is similar to trees. Gravity pulls water downhill, and as water flows, it carves channels that collect more water, leading to natural branching as the network develops over time. Coastlines are another famous example of fractal geometry in nature. In 1967, Benoit Mandelbrot published a paper titled "How Long is the Coast of Britain?", in which he pointed out that the measured length of a coastline depends on the scale at which you measure it. If you measure with a ruler that's hundreds of kilometers long, you'll get one answer. If you use a meter stick and trace all the little inlets and promontories, you'll get a longer answer. If you could measure at the scale of individual rocks or grains of sand, the coastline would be longer still. As you zoom in and measure at finer and finer scales, the measured length increases without bound. Coastlines aren't perfect fractals, obviously, but they have fractal-like properties over many scales, showing increasing complexity as you examine them more closely. Mountains and landscapes show fractal characteristics too. The outline of a mountain range viewed from a distance has a jagged, irregular quality. Zoom in, and individual peaks and ridges show similar jaggedness. Zoom in further to look at rock faces and boulders, and you see rough, irregular surfaces. Down to the grain and crystal level, the roughness continues. This self-similarity across scales is why computer-generated landscapes used in movies and video games often employ fractal algorithms. By starting with a simple shape and recursively adding fractal noise at different scales, programmers can generate realistic-looking mountains, plains, and terrain that look natural because they mimic the statistical fractal properties of real landscapes. Clouds are fractal, or at least they have fractal-like properties over a range of scales. A big cloud has a bumpy, irregular outline. Each bump itself has smaller bumps. Zoom in, and the turbulent boundary of the cloud shows similar structure at many levels. This is because cloud formation is driven by turbulent fluid dynamics, and turbulence naturally generates fractal patterns. The atmosphere is a chaotic system where motions at different scales interact in complex ways, and the result is a structure that looks similar whether you're looking at a large storm system from space or at individual wisps of cloud from the ground. Lightning bolts create fractal patterns as they branch and split on their path from cloud to ground. The electrical discharge follows the path of least resistance through the air, ionizing the gas and creating a conducting channel. But the air isn't uniform, and as the discharge propagates, it branches, exploring multiple paths simultaneously, creating that characteristic forked appearance. Thunder also has fractal properties, with the sound coming from different parts of the jagged lightning path, creating a complex acoustic signature. Even in our bodies, fractal patterns abound. Our lungs are a branching fractal structure, with the trachea splitting into bronchi, which split into bronchioles, which split into alveoli, the tiny air sacs where gas exchange occurs. This branching creates enormous surface area in a compact volume, allowing efficient oxygen uptake. Our circulatory system is another fractal network, with major arteries branching into arterioles, which branch into capillaries that reach every cell in the body, then rejoining into venules and veins to complete the circuit. The branching pattern maximizes surface area for nutrient exchange while minimizing the volume occupied by blood vessels. Our nervous system is yet another fractal network. Neurons have branching dendrites that receive signals and branching axons that send signals, creating complex networks that process information. The large-scale structure of the brain, with its folds and convolutions, has fractal properties, maximizing surface area of the cortex within the constraints of the skull. Some researchers have even found fractal patterns in the time series of heartbeats and brainwaves, suggesting that the rhythms of our body have self-similar structure across different timescales. Why does nature use fractals so extensively? Because fractal patterns arise naturally from growth processes, from optimization under constraints, from the dynamics of complex systems. A fractal branching pattern is often the optimal solution to the problem of distributing resources throughout a volume while using minimal material. Self-similar structures can be generated by simple local rules applied recursively, without needing a global blueprint or centralized control. This makes them ideal for biological systems that grow through repeated application of genetic instructions. Fractals also have the property of looking complex and natural while being generated by simple rules. This efficiency, the ability to create unlimited complexity from compact instructions, makes them powerful tools in nature's toolkit, and they allow structures to function across multiple scales simultaneously. A tree's branching works at the level of major limbs, at the level of twigs, and at the level of leaf veins, all following similar principles, but scaled to the appropriate size. As we lie here contemplating the fractal nature of the world around us, it's worth reflecting on what this means. The infinite patterns we've been exploring aren't just abstract mathematical curiosities. They're woven into the fabric of reality itself. When you look at a tree, a cloud, a mountain, you're seeing mathematics at work, seeing the consequences of simple rules playing out across scales, generating the complex, organic shapes that fill our world. Nature speaks the language of fractals, and by learning that language through mathematics, we gain a deeper understanding of the world's beauty. We've been exploring fractals and infinite patterns as geometric objects, things we can visualize and describe. But there's a deeper, more abstract aspect to these structures that reveals something profound about the nature of dimension itself. When we think of dimensions, we usually think of whole numbers. A line is one-dimensional. A plane is two-dimensional. The space we live in is three-dimensional. But fractals challenge this simple picture. They exist in dimensions that are not whole numbers, fractional dimensions that lie between the familiar integer dimensions we're used to. Let's think about what dimension really means, what it's measuring. One way to understand dimension is through scaling. Imagine you have a line segment of length 1. If you scale it by a factor of 2, making it twice as long, How many copies of the original would fit into the scaled version? 2 copies, obviously. Now take a square with side length 1, so it has area 1. Scale it by a factor of 2, making it a square with side length 2. How many original squares fit into the scaled version? 4, because area scales as the square of the length. Now a cube with side length 1, volume 1. Scale by factor 2. How many original cubes fit? 8, because volume scales as the cube of the length. Do you see the pattern? For a line, scaling by factor 2 gives you 2 to the first power copies. For a square, it's 2 squared, or 4 copies. For a cube, it's 2 cubed, or 8 copies. The exponent tells you the dimension. This leads to a general formula. If you scale a shape by a factor of r, and it takes n self-similar copies to cover the scaled version, then the dimension d satisfies the equation n equals r to the power d. Rearranging, we get d equals log of n divided by log of r. This is the definition of the similarity dimension, sometimes called the Hausdorff dimension, for self-similar fractals. Now let's apply this to the Sierpinski triangle. Remember, the Sierpinski triangle is made of 3 copies of itself, each scaled by a factor of 1/2. So n equals 3. R equals 2, because scaling up by 2 gives you the size where you can fit 3 copies. Plugging into our formula, the dimension is log of 3 divided by log of 2, which works out to approximately 1.585. The Sierpinski triangle has a dimension of about 1.6. It's more than a one-dimensional line, but less than a two-dimensional plane. It exists in a fractional dimension between 1 and 2. What does this mean intuitively? A curve that perfectly fills a plane would be two-dimensional. A simple straight line is one-dimensional. The Sierpinski triangle, with all its intricate gaps and structure, covers more than a simple curve would, but doesn't fill space like a plane does. Its dimension quantifies just how much of the plane it occupies, and the answer is a fractional amount, precisely 1.585 dimensional worth. Similarly, for the Koch curve, the single side of the Koch snowflake, we can calculate its dimension. Each stage of the construction replaces one segment with 4 segments, each 1/3 the length. So when we scale up by a factor of 3, we get 4 copies. That means n equals 4, r equals 3. The dimension is log of 4 divided by log of 3, which is approximately 1.26. The Koch curve is 1.26 dimensional. It's more than a simple one-dimensional line because of all its convolution and detail, but much less than two-dimensional. The Cantor set has dimension log of 2 divided by log of 3, which is approximately 0.631. It's more than a zero-dimensional set of isolated points because the points have structure. They're distributed in a particular self-similar way. But it's less than one-dimensional because it has 0 length. The Cantor set exists in a fractional dimension less than 1. These fractional dimensions aren't just mathematical curiosities. They tell us something real about the structure of these objects. They quantify complexity in a meaningful way. An object with higher fractal dimension has more structure, more detail, occupies its surrounding space more fully. Natural fractals, like coastlines and clouds, have measurable fractal dimensions that can be estimated from data, and these dimensions carry information about the processes that form them. For instance, fractal dimension has been used to classify different types of clouds. Cumulus clouds tend to have 1 fractal dimension, stratocumulus, another. The difference reflects different physical processes of formation and turbulence. Fractal dimension analysis has been applied to medical images, characterizing the texture of tumors or the density of blood vessel networks. In neuroscience, the fractal dimension of neural branching patterns can indicate health or disease. High-dimensional branching might indicate robust connectivity, while lower dimensions might suggest degradation. Fractal dimensions also appear in time series analysis. A graph of stock market prices over time, or temperature fluctuations, or heartbeat intervals can have fractal properties. The fractal dimension of these time series quantifies their roughness or smoothness, how much they vary across different timescales. Some researchers have found that healthy physiological systems show fractal fluctuations, suggesting that the body operates optimally with a kind of organized complexity that avoids being too regular or too random. The concept of fractional dimension is one of the most beautiful and mind-bending ideas in mathematics. It expands our understanding of what dimension even is, showing that the world is richer than the simple integer dimensions we're taught as children. Between the line and the plane, there's a whole continuum of possibilities, an infinite spectrum of fractional dimensions where strange and wonderful shapes live. When you think about the Koch snowflake or the Sierpinski triangle now, you can think of them not just as pretty patterns, but as objects that exist in their own fractional dimensions. Dimensions that we can calculate precisely using the simple formula relating copies and scaling. They're inhabitants of a strange in-between space, neither fully line-like nor fully plane-like, but something in between, something uniquely fractal. This idea of fractional dimension has inspired artists, architects, musicians. There are compositions where the rhythm or melodic structure has fractal properties, creating music that sounds natural and organic, complex but not random. There are buildings designed with fractal facade patterns, creating visual interest at multiple scales. The realization that dimension doesn't have to be an integer opens up new ways of thinking about structure, complexity, and organization. As you rest here, contemplating dimensions that aren't whole numbers, let your mind soften around this strange idea. We live in a three-dimensional world, or so we think. But perhaps our world is richer than that. Perhaps in the texture of things, in the patterns of clouds and trees and river networks, there are hints of these fractional dimensions, these in-between spaces where complexity dwells. The mathematical universe is larger and stranger than the simple geometries of Euclid, and infinite patterns with their fractional dimensions and self-similar structures are our guides to this expanded mathematical reality. We've been exploring patterns that go on forever, shapes with infinite boundaries, sets with zero measure but uncountable points. All of this talk of infinity has been leading us, perhaps inevitably, to confront infinity itself, not as a vague notion of very large or going on forever, but as a precise mathematical concept with properties that can be studied and understood. Let's take a moment to think about what infinity really means, how mathematicians have tamed this wild concept, and what it tells us about the universe of numbers. The ancient Greeks had a complicated relationship with infinity. They used the concept, certainly. They knew that the counting numbers go on forever. They proved that there are infinitely many prime numbers. but infinity made them uncomfortable, philosophically. The Greek mathematical tradition preferred the finite, the bounded, the complete. Infinity was seen as potential, something that could grow without limit, but never actually reached, never completed. The idea of a completed infinity, an actually existing infinite collection, was problematic. It wasn't until the late 19th century that a mathematician named Georg Cantor developed a rigorous theory of the infinite, a way to reason about infinite sets with the same precision mathematicians used to reason about finite ones. Cantor's work was revolutionary and controversial. Some of his contemporaries called his ideas about infinity a disease from which mathematics must recover. Others recognized it as profound and foundational. Today, Cantor's set theory is the basis for much of modern mathematics, and his insights into infinity are considered among the most important discoveries in the field. Cantor showed that not all infinities are the same. There are different sizes of infinity, and some infinite sets are larger than others in a precise, meaningful sense. Let's explore this gently, building up the ideas step by step. Consider the counting numbers 1, 2, 3, 4, and so on forever. This is an infinite set, obviously. We can never list all of them because there's no last number. Now consider the even numbers 2, 4, 6, 8, and so on. This is also infinite, but intuitively, it feels like there should be half as many even numbers as total counting numbers, right? After all, we're skipping all the odd numbers. But Cantor showed that this intuition is wrong. The even numbers and the counting numbers have the same size in a technical sense. How? By showing that you can pair them up 1 to 1 with none left over. Match 1 with 2, match 2 with 4, match 3 with 6, and in general, match n with 2n. Every counting number gets matched with exactly one even number, and every even number gets matched with exactly one counting number. This one-to-one correspondence, what mathematicians call a bijection, shows that the two sets have the same cardinality, the same infinite size. This same trick shows that there are just as many integers, including negative numbers and 0, as counting numbers, even though the integers seem like a much bigger set. It shows that there are just as many rational numbers, fractions, as counting numbers, even though between any two counting numbers, there are infinitely many fractions. All these sets are countably infinite, meaning you can list their elements in a sequence, matching them 1 to 1 with the counting numbers. But then Cantor proved something shocking. The real numbers, all the numbers on the number line, including all the irrational numbers like pi and the square root of 2, cannot be put into 1-to-1 correspondence with the counting numbers. There's no way to list all the real numbers. They form an uncountable infinity, a larger infinity than the counting numbers. Cantor's proof of this, his famous diagonal argument, is a masterpiece of logical reasoning. It shows that any attempted list of real numbers must necessarily leave some out, proving that the real numbers are more numerous than the counting numbers, even though both are infinite. This means there are at least two different sizes of infinity: countable infinity, like the counting numbers, and uncountable infinity, like the real numbers. But Cantor went further. He showed that given any infinite set, you can always construct a larger infinite set. There's no largest infinity. The hierarchy of infinities goes on forever. Itself an infinite hierarchy. This is where set theory gets truly mind-bending. There are infinitely many different sizes of infinity, each one strictly larger than the one before, extending upward without end. What does all this have to do with our infinite patterns, our fractals and self-similar sets? Well, remember the Cantor set. We showed that it has zero measure, meaning its total length is zero, yet it's uncountable. It contains just as many points as the entire real line, even though it's scattered across the line in this highly disconnected way. The Cantor set is a beautiful example of an uncountable infinity hiding in zero space. It shows that size and number can come apart in the realm of the infinite. The Mandelbrot set's boundary is also uncountable, containing infinitely many points arranged in that infinitely intricate structure. When we zoom into the Mandelbrot set and find miniature copies nested within it, we're seeing infinity within infinity. Infinite complexity at every scale. The fact that this emerges from such a simple rule, z goes to z squared plus c, is a reminder that infinity is accessible, studyable, arising naturally from simple processes. Infinity in mathematics isn't a single monolithic concept. It's a rich hierarchy of different sizes, different types, different properties. There's the potential infinity of the counting numbers, always having one more. There's the completed infinity of the infinite set of all counting numbers considered as a whole. There's the larger, uncountable infinity of the continuum, the real numbers. There are infinities of different orders, measured by the cardinalities Cantor defined. And there's infinity in terms of limit processes, like the infinite iterations we perform to construct our fractals. When we build the Koch snowflake, we're taking a limit as the number of iterations goes to infinity. The actual Koch snowflake is this limit object, the shape that emerges after infinitely many steps. It doesn't exist at any finite stage of construction. It only exists in the limit. This is a subtle but important point. The infinite pattern isn't just a very complicated finite pattern. It's qualitatively different. It has properties like infinite perimeter and finite area that no finite approximation has. The limit isn't just the next step in the sequence. It's a fundamentally different kind of object. This concept of limits is central to calculus, to analysis, to much of modern mathematics. When we take the derivative of a function, we're taking a limit of ratios as the denominator approaches zero. When we integrate, we're taking a limit of sums with infinitely many terms. Mathematics has developed sophisticated tools for dealing with infinity, for making it precise and tractable. Infinite patterns are one area where these tools shine, allowing us to construct and understand objects of genuine infinite complexity. As you rest here, thinking about infinity, let it expand in your mind. Infinity isn't just a really big number. It's not even just bigger than any finite number. It's a whole landscape of concepts, a family of ideas ranging from the countable to the uncountable, from the potential to the actual, from the limit process to the completed whole. And our infinite patterns, our fractals and self-similar sets, are beautiful examples of infinity made concrete, infinity that we can visualize, study, and understand. They're bridges between the finite world we inhabit and the infinite mathematical universe that underlies it. Throughout this journey, we've been exploring infinite patterns as mathematical objects, abstract constructions defined by precise rules, and analyzed with rigorous logic. But these patterns have a life beyond pure mathematics. They've found applications in science, technology, art, and everyday life in ways that their discoverers could never have imagined. Let's explore how these infinite patterns, born in the realm of mathematical abstraction, have come to shape the world around us in practical and surprising ways. One of the most widespread applications of fractals is in computer graphics. Before fractal geometry, creating realistic natural scenery in computer-generated images was incredibly labor-intensive. Artists had to painstakingly model every rock, every tree, every cloud, treating each as a separate object with its own detailed geometry. But fractal algorithms changed everything. By using recursive subdivision with carefully tuned randomness, programmers can generate realistic mountains, forests, and landscapes with relatively little code. The key insight is that natural objects have fractal-like properties, so mimicking those properties produces realistic results. A mountain range can be generated by starting with a simple triangular mesh and recursively subdividing it, adding random displacement at each level of subdivision scaled appropriately to create roughness at all scales. The result looks like a natural mountain because it has the same statistical self-similarity that real mountains have, shaped by erosion and geological processes that work at many scales. Every big-budget movie with computer-generated landscapes, every video game with procedurally generated terrain, every virtual reality environment uses fractal algorithms extensively. Fractals have also revolutionized data compression. Traditional image compression algorithms like JPEG work by breaking an image into small blocks and encoding each block separately. But fractal compression uses self-similarity. If part of an image looks similar to another part, just at a different scale or orientation, then instead of storing both parts fully, you can store one and a transformation that generates the other. Images with fractal-like properties, which includes most natural images, can be compressed very efficiently this way. While fractal compression hasn't completely replaced other methods, it's a powerful tool in the arsenal of compression techniques. In telecommunications, fractals appear in the design of antennas. Fractal antennas use self-similar geometry to create antennas that are compact yet effective at multiple frequencies. A traditional antenna is usually designed for one frequency or a narrow range of frequencies. But a fractal antenna, with its structure that repeats at multiple scales, can interact with electromagnetic waves of different wavelengths, making it broadband. These antennas are smaller than traditional designs while maintaining good performance, making them ideal for modern wireless devices where space is at a premium. Your cell phone might well have a fractal antenna inside it. Medical imaging has benefited from fractal analysis. The texture and structure of tissues often have fractal properties, and characterizing the fractal dimension of tissue can help in diagnosis. For instance, cancer cells may have different fractal properties than normal cells. The branching pattern of blood vessels in a tumor can be analyzed using fractal geometry to assess how aggressive the tumor is. In radiology, fractal analysis of bone structure in X-rays can help detect osteoporosis earlier than traditional methods. The complex branching of neurons and blood vessels in the brain has been studied using fractal geometry to better understand normal development and disease. Environmental science uses fractals to model and understand natural systems. Forest growth, wildfire spread, river network development, all can be modeled using fractal-based algorithms. These models help predict how ecosystems will respond to changes, how pollutants will disperse, how land use changes will affect watersheds. The irregular geometry of natural boundaries, coastlines, and terrain is better captured by fractal models than by classical, smooth, geometric models. In economics and finance, researchers have discovered that market prices and other financial time series show fractal properties. Benoit Mandelbrot himself worked extensively on applying fractal geometry to economics, showing that price fluctuations have a kind of self-similarity across timescales. A graph of price changes over one day looks statistically similar to a graph over 1 month or 1 year. This has implications for risk modeling and investment strategies. Traditional financial models often assume smooth, well-behaved statistical properties, but real markets are rougher, more volatile, with more extreme events than these models predict. Fractal models better capture this reality, though they also reveal how difficult accurate prediction is in these complex systems. Artists have embraced fractals enthusiastically. Fractal art, generated using computers to visualize mathematical fractal sets or to create fractal-inspired patterns, has become a recognized art form. The visual beauty of fractals, with their infinite detail and organic appearance, makes them natural subjects for artistic exploration. Some artists have used fractal algorithms to generate sculptures, architecture, and jewelry. The natural aesthetic appeal of fractals suggests they tap into something deep in human perception. Perhaps the same pattern recognition abilities that evolved to navigate natural environments full of trees, clouds, and rivers. Music composition has also been influenced by fractals. Composers have created music where the rhythm or melodic structure has self-similar properties, repeating motifs at different timescales. Some traditional music from various cultures has been analyzed and found to have fractal properties, suggesting that fractal structure in music might be naturally appealing or memorable. The relationship between fractals and aesthetics, whether visual or auditory, is an ongoing area of research, exploring why certain mathematical patterns feel beautiful to us. In network design, whether it's the internet, power grids, or transportation networks, fractal-like structures often emerge or are deliberately designed. A fractal network can be efficient, resilient, and scalable. The branching structure allows local areas to be connected directly, while also providing paths to more distant destinations through hierarchical routing. Understanding the fractal properties of real-world networks helps engineers design better systems and predict how they'll behave under stress. Even in quantum physics, fractals have appeared in unexpected places. The energy levels of certain quantum systems have fractal structure. Quantum fractal behavior has been observed in electron paths, in strong magnetic fields, and in the patterns of quantum chaos. This deep connection between fractals and quantum mechanics is still being explored, hinting that fractal geometry might be fundamental to nature at the most basic level. What all these applications show is that fractals and infinite patterns aren't just mathematical games. They're useful, powerful tools for understanding and shaping the world. The same self-similar structures we've been exploring geometrically appear in time series data, in the texture of materials, in the organization of complex systems. By learning the language of fractals, mathematicians have given scientists and engineers a new way to describe and work with complexity. And this brings us back to the beauty we've been contemplating. The fact that these patterns are both beautiful to look at and useful for solving real problems suggests something profound, that there's a deep harmony between mathematics and reality, that the patterns we find beautiful are often the patterns that nature uses, that aesthetic and practical value can align in unexpected ways. We've traveled far tonight, from simple geometric transformations to the shores of infinity itself, exploring patterns that never end, shapes that live in fractional dimensions, sets that occupy zero space yet contain uncountable points. We've seen how simple rules applied repeatedly can generate unlimited complexity. We've glimpsed the strange and beautiful mathematical objects that exist in the limit of infinite iteration. And we've discovered that these abstract patterns have echoes in the natural world and applications in practical domains. What have we learned? Perhaps the most important lesson is about the relationship between simplicity and complexity. The fractals we've explored, the Koch snowflake, the Sierpinski triangle, the Cantor set, the Mandelbrot set, all arise from remarkably simple rules. The Koch snowflake: divide each segment into 3, replace the middle third with a triangular bump. The Sierpinski triangle: remove the central quarter of each triangle. The Cantor set: remove the middle third of each interval. The Mandelbrot set: iterate z goes to z squared plus c, and see if it stays bounded. These rules are so simple that a child could understand them, could perform the first few iterations. Yet from these simple beginnings, infinite complexity emerges. Not random, chaotic complexity, but structured, patterned complexity. Beauty emerges. And this suggests something profound about the nature of complexity itself. Perhaps complexity doesn't require complicated rules. Perhaps the most interesting complexity, the complexity we find beautiful and meaningful, arises from simple rules applied consistently, patiently, infinitely. This has implications beyond mathematics. In biology, the complexity of living organisms arises from relatively simple genetic rules applied during development. A cell doesn't contain a complete blueprint for the organism in every detail. It contains instructions, rules for how cells should divide and differentiate, how tissues should form and organs should develop. These rules are applied recursively as the organism grows, leading to complex structures with that same kind of hierarchical self-similarity we see in fractals. The branching of blood vessels, nerves, and airways, the folding of the brain, the structure of the skeleton, all emerge from developmental rules that are local and relatively simple, but that generate global complexity through iteration. In evolution, simple rules of variation and selection, applied over vast stretches of time, generate the immense diversity and complexity of life on Earth. In economics, simple rules followed by many individuals can lead to complex market behaviors. In society, simple social rules and norms, propagated through culture and imitation, create complex social structures. The pattern we've been exploring mathematically might be a pattern that appears throughout reality. Simplicity generating complexity, local rules generating global structure, iteration generating infinite detail. There's also a lesson here about limits and infinity. The true infinite patterns we've explored don't exist at any finite stage. The Koch snowflake with infinite perimeter, the Sierpinski triangle with zero area, the Cantor set with uncountable points. These are limit objects. They only fully exist after infinite iterations. But we can approximate them, get arbitrarily close with finite constructions. And in many cases, a finite approximation is good enough for practical purposes. A computer-generated mountain doesn't need infinite subdivision. A few levels of fractal detail make it look realistic. A model of a river network doesn't need to trace every tiny rivulet. A few levels of branching capture the essential structure. This suggests a useful way of thinking about infinity as a limit that guides us, a direction we can move in, even if we never fully reach it. In mathematics, we work with infinity rigorously through limit processes. In the real world, we can use infinite patterns as idealized models that give us insight, even though physical reality has limits at some scale. The concept of infinity helps us think about what would happen if we could keep going, what structure would emerge in the limit, and that understanding helps us even when we're working at finite scales. The patterns we've explored are also a reminder that mathematics is about more than calculation. Yes, we can calculate the area of the Koch snowflake, the dimension of the Sierpinski triangle, the cardinality of the Cantor set. But beyond the calculations, there's wonder. There's the sheer improbability of these objects, the fact that they exist in the mathematical universe at all. There's the beauty of their structure, the elegance of their self-similarity. There's the surprise of infinite perimeter with finite area, or zero measure with uncountable points. These aren't just solutions to homework problems. They're glimpses of a strange and wonderful mathematical landscape. For those of you drifting towards sleep, let these patterns linger in your mind. Imagine zooming into the boundary of the Mandelbrot set, descending through layers of spirals and tendrils, finding miniature copies nested within copies, pattern within pattern, forever. Or picture the Sierpinski triangle, its internal structure revealed with each iteration. Solid triangles arranged in that perfect hierarchical pattern, gaps and shapes repeating at every scale. Or think of the Cantor set, scattered across the number line like dust, yet containing as many points as the whole line. A perfect set with no interior, a nowhere dense set that's nevertheless uncountable and rich with structure. These patterns exist in the realm of pure mathematics, which is, in some sense, a realm of pure thought. They don't exist in the physical world in perfect form. You can't hold a Koch snowflake or touch the Mandelbrot set. They're abstractions, ideal forms that we can contemplate and study, but they reveal truths about pattern, structure, complexity, and infinity that transcend their abstract origins. They show us possibilities, new ways of thinking about space, dimension, and form. They expand our conceptual vocabulary, giving us new ways to describe and understand the world. And perhaps most importantly, they're beautiful. Not beautiful in a purely aesthetic sense, though many people find them visually stunning, but beautiful in a deeper way. Beautiful in the sense that they reveal unexpected connections, elegant structures, profound truths. Beautiful in the way that a perfect proof is beautiful, or a deep insight, or a moment of understanding. They have that quality of rightness, of inevitability, of being exactly as they should be. The infinite patterns we've explored tonight are monuments to the power of human thought, to our ability to grapple with infinity, to tame the wild concept of endlessness and make it precise, studyable, beautiful. We've come to the end of our journey through infinite patterns, though of course these patterns themselves never end. They continue forever, spiraling inward and outward, revealing new structure at every scale, existing in that strange mathematical space where the finite and infinite intertwine. I hope this exploration has given you a sense of wonder at the depth and beauty of mathematics, at the strange objects that live in the mathematical universe, waiting to be discovered and understood. As you settle into rest, perhaps you'll carry some of these images with you into your dreams. The Koch snowflake, with its infinitely detailed boundary enclosing a modest, finite space. The Sierpinski triangle, eating itself recursively, becoming more gap than substance, yet never quite disappearing. The Cantor set, scattered infinitely yet occupying no space. The Mandelbrot set, that black beetle shape with its infinitely intricate boundary, hosting miniatures of itself nested endlessly deep. These patterns remind us that infinity is not an enemy of understanding. Infinity can be tamed, studied, made precise. Through careful definition and patient reasoning, mathematicians have learned to work with the infinite as comfortably as with the finite, and they've discovered that the infinite world is far richer than anyone imagined. Between 1 and 2, between the line and the plane, there's an entire spectrum of fractional dimensions. Beyond the countable infinity of the integers, there are larger, uncountable infinities, and beyond those, still larger infinities, an endless hierarchy of infinite sizes. The patterns we've explored are not the end of the story, but the beginning. Fractal geometry continues to develop as a field, finding new applications and revealing new connections. Researchers continue to explore the Mandelbrot set and related fractals, discovering new structures, new properties, new depths. The relationship between fractals and chaos theory, between fractal dimensions and statistical physics, between fractal patterns in nature and the mathematical underpinnings of reality, all these remain active areas of investigation. If you've enjoyed this gentle mathematical journey, if you found wonder in these infinite patterns, then I hope you'll join us again. There's so much more to explore in the world of mathematics. So many beautiful ideas, elegant proofs, surprising connections. Mathematics is not just a tool for calculation, though it certainly is that. It's a way of seeing, a lens through which we can perceive patterns and structures that would otherwise remain hidden. And it's a source of profound beauty, of intellectual satisfaction, of moments of genuine awe at the elegant architecture of the mathematical universe. Thank you for spending this time with me, for letting your mind wander through these infinite patterns. If you found value in this exploration, a like and subscribe would mean a great deal and helps this channel continue creating these soothing mathematical journeys. Share it with friends who might appreciate a different kind of bedtime story, one that engages the mind while calming it, that invites wonder while promoting rest. From the world of infinite patterns, where boundaries stretch forever and structures nest endlessly, where zero can contain infinity and finite can embrace infinite, I wish you peaceful rest. May your dreams be filled with beautiful patterns, self-similar and harmonious. And may you wake tomorrow with a renewed appreciation for the mathematical beauty that surrounds us, hidden in trees and clouds, in coastlines and rivers, in the very fabric of space and time. Good night.